Hello fellow problem solvers. So today we're going to be doing one of my top 10 favorite functions of all time, problem from the 2010 IMO Shortlist, problem A6. To be able to solve this problem, the only thing you really need to know is what functional equations are, and you need to have at least some experience solving them. If you want to try this problem out on your own, I suggest you try it out for a minimum of an hour, ideally 3 hours, but not more than 4.5 hours. If, on the other hand, you would like to go along with us, I suggest you read the problem and try it out for 30 minutes. So now, let's begin. Before I summarize the problem and before we begin the problem-solving process, I just want to point out that this is one of my favorite functional equations of all time. And given that, I will complement this problem a lot. So to summarize, what we have are two functions, f and g, from the positive integers to the positive integers, which satisfy f of g of n is equal to f of n plus 1 for all positive integers n, and symmetrically for g. And we need to prove that these functions f and g are really the one and the same functions. Now, there's many approaches to solving these types of problems, but the first sort of thing is that we need to explore the problem. We need to get comfortable with it, play around, and get some ideas out on paper. And we'll only get that by exploring and asking questions, and also taking note of the things we notice. The art of problem solving is to notice certain things that might not look like a big deal, but turning them into a big deal. So here, the first thing I would actually do to start a problem is actually try to see what sort of function are we dealing with, i.e. if f is equal to g, then the function we're really dealing with is the function f of n is f of n plus 1. So the first question I have here is, what are the solutions to this functional equation? Because if we find the solutions to this functional equation, then we know what we can and cannot prove here in our problem. I suggest you take 5 minutes to try to find all the solutions to this functional equation. So what we have here is, if f of n is equal to some number, say a, then for that a, we have f of a is equal to a plus 1. And then if we plug in a instead of n, we'll get f of a plus 1 is a plus 2. And plugging in a plus 1 instead of n, we'll get f of a plus 2 is equal to f of a plus 1 plus 1, which is a plus 3. And so on. So that means that if we have one value, if f of n is a, then for all numbers greater than or equal to a, we have f of x is x plus 1. So the thing that makes sense here is first saying, okay, let's take the minimum a such that f of n is equal to a. In other words, of all the possible values that f takes, let's take the smallest such value. And such a value exists because we are in the positive integers to the positive integers. And such a value exists by the well-ordering principle. Now, if that value is, say, b, so if the minimum of f of n from n equals 1 to infinity is b, then we have f of b is equal to b plus 1, and f of n is equal to n plus 1 for all n greater than or equal to b. Now, what if a value is less than b? Pause for 30 seconds and try to see what that means. Well, it means that regardless of this, we know that f of n is going to be greater than or equal to b, because b is the smallest value that f takes. And ergo, by this thing right here, by plugging in instead of n, plugging in f of n, we'll have f of n is f of n plus 1. Now this might seem like magic at first, and it did to me, but what it tells us really is that once we set the smallest value b, all the numbers less than b can really have their f point to anything greater than or equal to b, and we will still have a functional solution. The only thing that must hold is because b is the smallest one, and all numbers greater than or equal to b are going to their f's are going to be greater than or equal to b plus 1, that means at least one of these numbers less than b must be equal to b. But other than that, we can have any other solution. So we can put, say, f of 1 to be 1000, f of 2 to be 4, f of 3 to be 81, and then f of 4 is 5, and f of n is n plus 1 for all n greater than or equal to 4. And that's a solution. That's a perfectly valid solution to the functional equation. Now, what does this family of solutions to f of n equals f of n plus 1 tell us about what we can or can't prove right here in our problem? It tells us that we won't be able to really prove an injection, at least not if we're looking at the numbers less than b, the smallest possible value f outputs. However, we do know that if we're plugging in stuff that are greater than b, if we're plugging in x and y, which are both greater than b, then we know that both of those f's are going to go to x plus 1 and y plus 1, but we know that they're injective, so that can be something that we could maybe work towards. Nonetheless, now let's explore our actual problem. Say, what we first notice is because f and g are symmetric. That means that if we get something for f, we will probably need to get this a similar or same thing for g. So let's first look at what can we see. Say, what happens if two f's are equal if f of x is equal to f of y? Take 2 minutes to figure out what this means. Well, what it means is if we plug in x here, we will get that g of f of x is equal to g of f of y. However, both of these g's are equal to g of x plus 1, and this one's equal to g of y plus 1. So in other words, if we have f of x equal to f of y, then we know the same thing holds for g of x is equal to g of y. Because f and g are symmetric, we can get the same result the other way. This is an if and only if right here. Is this useful? We don't know, but it's something we notice, and let's keep track of it. So, what's another thing you may notice? Well, if f of x is equal to x for some x, then we'd get a contradiction straight up, because then we'd have plugging it here in the second equation. Let's call this the second equation and the first equation. Plugging x into the second equation would give us g of x is equal to g of x plus 1, which is absurd. So now, from here, we know that f of x is different from x for all positive integers x. Now, before I go forward exploring, I suggest you take 5 before I sort of show what the next hint is. Take 5 minutes now, and let's go. So we have these two things. Now we can also see that if we plug in, instead of n, we put g of n. In the first equation, we'd have f of g of n is equal to f of g of n plus 1 is equal to f of n plus 2. In other words, we can, if we put in a bunch of g's, say we put g of g of g of g of n, k times g of n, we'd get that this is going to be equal to f of n plus k. Now what this tells us is that if we get f of n being equal to some value a, then we will have a positive integer n, some other n, such that it is equal to a plus k, where k is any positive integer. And the same thing also holds for g. Now, drawing inspiration from how we solved f of n is equal to f of n plus 1, it would make some exploratory sense to look at the smallest value f takes and the smallest value g takes, and then try to perhaps equalize them. So what we have is that if the smallest value that f of n for all n that go from 1 till infinity is a, and the smallest value that g of n takes from 1 to infinity is b, then what we have is that sort of the set f of n from 1 till infinity equals the set a, a plus 1, and so on, having all the natural numbers from a till infinity. And the same thing holds for g. They cover all the natural numbers from b up till infinity. And the reason we know this is because of this thing right here. If we have an a, then we'll have an a plus k for any positive integer k. Now I invite you to take between 10 and 20 minutes to see if you can combine any of these things. If any idea comes to mind, take 10 minutes now. So the idea is, let's look at this equation right here. We know that f of x is equal to f of y if and only if g of x is equal to g of y. Now, taking inspiration from before, we know that in the solution for f, this is injective if both x and y are greater than a in this case and b in this case. So now let's see if we can work with that. Say that both x and y are greater than or equal to a. Now, how can we use this? Take 2 minutes to figure it out. Well, here's the thing. If x and y are greater than a, that means that there exists some integers, m and n, both positive, such that f of m is equal to x and f of n is equal to y. Now, what does f of x equal f of y give us? Well, it gives us g of x is equal to g of y, or when we rewrite them in terms of f's, it gives us from f of x is equal to f of y, we get that g of f of m is equal to the g of f of n. And here's where the magic happens. This gives us from the second equation that this is g of m plus 1 is equal to g of n plus 1, i.e. g of m is equal to g of n. And now, going back here, this gives us f of m is equal to f of n. But because f of m is x, and f of n is y, this gives us x equals y. Now, isn't that amazing? It's so simple, but so stunning. This is one of the reasons I love this problem. The simplicity and the beauty of it is immense. So now that we have this, we really have injection on x and y greater than or equal to a. And the great thing is that we have this injection for g as well. Because if we have g of x is g of y, where x and y are greater than or equal to a, and say they are not greater than or equal to b, then we can just move on to f and we'll get the same result, i.e. x equals y. So what this phenomenal fact means is that the functions are injective on the range from the smaller of a and b. So if x and y are greater than or equal to the smaller of a and b, then we can say from f of x equals f of y that it follows x equals y. So now take at least 10, ideally 30 minutes trying to push the problem forward. Play some more, explore some more, see what you can do with this. This is an absolutely spectacular problem. And now I invite you to pause. So let's go on to the next idea. So now we have all these facts that we figured out from the problem. Now we know that a and b should be equal if the problem statement is true. So now let's see if we have enough tools and facts to prove that a and b must be the same. Now if you were doing something else here, I really invite you to try and prove this for 10 minutes at minimum. I am telling you, this is a spectacularly beautiful problem, and it will be a shame to not try it out fully. So now the beautiful idea is, assume a is greater than or equal to b. Now we know that f of a isn't going to be equal to a, so it's at least a plus 1, which means in fact that we can write it as f of some t plus 1. The reason we can do that is because f of a minus 1 is greater than or equal to a, so such a t exists. Now, this, in fact, is equal to f of g of t. And now what we have is that f of a is equal to f of g of t. And now by our injection, numbers which are greater than or equal to b, we have that a must be equal to g of t. Now, this doesn't really give us anything, but if we apply the same sort of trick to b, we get that there is g of b is greater than or equal to b plus 1, which means there exists some u such that g of b is equal to the g of u plus 1, which is equal to g of f of u. And by the same logic, f of u and b are both greater than or equal to b because they're in range. So b must be equal to f of u. However, f of u is greater than or equal to a. And now we have a is greater than or equal to b on one hand, but on the other hand, b is greater than or equal to a. So this implies that a is equal to b. This is a beautiful, beautiful find. Now, I invite you to pause for 10 to 20 minutes and try to take the problem further. Pause now, and now let's go further. So the next focus would be to try to prove that f of a is equal to a plus 1. And by just pure symmetry, this would also be equal to g of a. And here is where I would invite you to try and prove this for at least 10 minutes if you haven't tried so already. Please pause now. Well, as many great proofs in mathematics, let's just assume the contrary and let's see what happens. So we know that f of a is not equal to a, and say it's not equal to a plus 1 either. Then we know f of a is greater than or equal to a plus 2. Now, how can we use this fact? Pause for 2 minutes and try to figure out a creative way to use this. Well, it's a little bit similar as before. We know that f of a minus 2 is greater than or equal to a, which means that there exists some z such that f of z plus 2 is equal to f of a. Now here is where the kicker is, namely f of z plus 2 is equal to f of g of z. Now we have that there exists a z such that g of z is equal to a by the induction on integers greater than or equal to a. Now take 2 minutes and figure out, can we do anything with this? I hope you took the 2 minutes because, and this is absolutely mind-blowing for me, g of z is in range, in the same range f is in. So there exists some t such that f of t is equal to g of z, and ergo g of f of t is equal to a on one hand. But on the other hand, this thing right here is equal to g of t plus 1. And now from here it follows that g of t is equal to a minus 1. Now this is absurd because we assumed that a was the smallest member of the image of g and f. And this here is a contradiction, which means that f of a isn't greater than or equal to a plus 2, and because it's not equal to a, this implies that f of a is equal to a plus 1. And in the same way, g of a is equal to a plus 1. Now take 5 to 15 minutes and try to finish the problem. So here's the finish. Now from f of a is a plus 1 is g of a, if we plug that into the first equation, what we get is f of, so g of a plus 1, so we get f of a plus 1 is equal to f of a plus 2. And then we get, similarly, g of a plus 1 is equal to a plus 2. And then we plug in a plus 1 in both of these. And we'll get f and g of a plus 2 are both equal to a plus 3. And via induction, what we get is that f of n is equal to n plus 1 for all n greater than or equal to a. And in the same way, this is also equal to g of n. The induction is done simultaneously. We prove simultaneously that both f of n and g of n are n plus 1. And now we're left with showing that f of n and g of n are equal for all n less than a. So for all n less less than a, we need to show that f of n is equal to g of n. And how do we do that? Take 3 to 7 minutes and try to figure this out. Well, similar as before, if n is less than a, then we know that f of n is going to be greater than or equal to a. And because of that, by this thing right here, we know that f of n is going to be f of n plus 1. But so is g of f of n. But g of f of n is equal to g of n plus 1, which means that g of n and f of n are equal. Now this concludes the problem because it shows that f of n is equal to g of n for all natural numbers n. Now let's bring it all together, summarize it, and write up the solution. So we started off with this, and our first sort of lemma was that f of x is equal to f of y if and only if g of x is equal to g of y. And we proved this because if f of x is f of y, then it follows that g of f of x is g of f of y. And this is true if and only if g of x plus 1 is g of y plus 1, which is true if and only if g of x is equal to g of y. And the other case follows similarly. And now we prove lemma 2. If a is the minimum of the set f of 1, f of 2 up till infinity, and b is the minimum of the set g of 1, g of 2 up till infinity, we have that if x and y are greater than or equal to the smaller of a and b, then f of x equals f of y implies that x equals y. So assume both x and y are greater than or equal than the minimum of a and b, and assume without loss of generality that a is greater than or equal to b, because this would also hold true for g of x and g of y. Now here we can say that if x and y are greater than or equal to b, we know that there exists some c and d such that g of c is equal to x and g of d is equal to y. And now from f of x equals f of y, we immediately get that f of g of c is equal to f of g of d. And from here, we get that f of c is equal to f of c plus 1 is equal to f of d plus 1. And from here, we get that via lemma 1, that g of c is equal to g of d. And by the definition of c and d, we get that x is equal to y. Now with these two lemmas, we move on to proving the claim a is equal to b. Because f of a isn't equal to a, we know f of a is going to be greater than or equal to a plus 1. And the reason we know this is because if f of x is equal to x, then it follows that g of x is equal to g of x plus 1, which is a contradiction. Now, f of a is greater than or equal to a plus 1, which means that f of a minus 1 is greater than or equal to a. So there exists a e such that f of e is equal to f of a minus 1. Now this means that f of a is equal to f of e plus 1, which is f of g of e. And now, via lemma 2, this implies that a is equal to g of e. But we know that g of e is greater than or equal to b. In an analogous manner, we get that there exists a h such that b is equal to f of h, which is greater than or equal to a. And from here, we get that a must be equal to b. And now we prove our second claim, namely that f of a is equal to g of a is equal to a plus 1. And the way we do that is, assuming it's not, then we know that f of a is greater than or equal to a plus 2. And so it follows that there exists a z such that f of z plus 2 is equal to f of a. Now this here implies that f of g of z is equal to f of a. And now by lemma 2, we get that g of z is equal to a for some z. Now, because a and b are equal, there exists some w such that g of z is equal to f of w. And this then transforms into g of f of w is equal to a, but on the other hand, this is equal to g of w plus 1. And here we would get that g of w is equal to a minus 1, which is impossible because a is the smallest number that is in the image of f and g. And that's just what that is. It's the image of f and g. So from here, it follows that f of a is strictly less than a plus 2, but because a is the smallest one and it's not equal to a, this implies f of a is equal to a plus 1. And in the same manner, this is equal to g of a. And now we top it off. So now, via induction, we prove that for all n greater than or equal to a that are in the positive integers, that f of n is equal to g of n is equal to n plus 1. So we have our base that we've just proved, that f of a is equal to g of a is a plus 1. Assume f of k is equal to g of k is k plus 1. Then plugging k in both the first and the second equation, we get that f of k plus 1 is equal to k plus 1 plus 1, which is k plus 2, and g of k plus 1 is equal to k plus 1 plus 1, which is k plus 2. And this concludes our induction. So now we know that f of n is going to be n plus 1, and this is also going to be equal to g of n for all n greater than or equal to a. And now we've proved the problem statement for all n greater than or equal to a. However, if n is less than a, then we know that f of n and g of n are both greater than or equal to a. And as such, we know that f of g of n, plugging it in here, is equal to g of n plus 1. But also, by our first equation, this is equal to f of n plus 1. And just via that, we get f of n is g of n for all n less than a as well. This concludes our problem statement. QED, we proved what we wanted to prove. And as always, thanks for problem solving.